we've seen how data gets from one computer to another, whether the computers are on the same network or different networks connected by a LAN or WAN. Now let's take a look one level deeper. How does data get from one application program on a sending computer to a suitable application program on the receiving computer? When you send an email, your computer most likely sends the data using the Internet Protocol, which we discussed earlier in this course. As we saw, routers use the destination IP address and routing tables to route a packet through the network and get it to the correct host. We learned that before sending the packet to the next hop, a router encapsulates the packet in a frame that includes a Layer 2 address. Switches use this address to reach the next hop, where the process repeats until the packet reaches the destination. This process delivers the data to the correct computer. But what happens then? A computer will most likely have more than one application program running. So once the data arrives, how does it get to the correct application? Nothing in the IP header identifies which application program on the computer should receive the data. And once the data is sent, how does the sending computer know that the data arrives successfully and in the correct order? In this section, we'll answer all these questions. Let's return to our postal analogy for just a moment. Earlier we saw that once a letter gets delivered to the correct house, its journey is not complete. Because more than one person can reside at the same address, the recipient's name must also be present in the address on the envelope. The same is true when data arrives at a destination computer. Data gets routed to the correct computer with the help of IP and other lower layer protocols such as Ethernet. But once there, its journey isn't complete. One of the jobs of transport layer protocols is getting the data from one application program on one computer to the correct application program on another. Transport layer protocols enable true end-to-end or application-to-application communication. Transport layer or layer 4 protocols, such as the User Datagram Protocol or UDP and the Transmission Control Protocol or TCP, bridge the gap between the lower layers, which are responsible for data delivery, and the application layer, which interacts with application programs. You might remember UDP and TCP from our discussion early in the course on protocols in general. Both UDP and TCP use software ports to help route data to the correct application program. The destination port number is analogous to the name in a letter's address and provides a way of getting the data to the correct application layer protocol and ultimately the correct application program. The source port is like the name in the return address and uniquely identifies the connection on the sending side. Remember the concept of multiplexing from the last section on WANs? Multiplexing is where multiple sources of data, such as phones, fax, and computers, combine into a single stream over a single line. Well, the transport layer also multiplexes data. The screen shows 3 different application layer protocols on both the sending computer and the receiving computer. UDP and TCP provide a way of combining or multiplexing data from many application programs into a single stream using the same IP address. Notice that each application layer protocol receives a unique numerical identifier or software port, which is different than a physical or hardware port. As we'll see in a moment, UDP and TCP use these software ports to route data to the appropriate application. The examples shown on screen are common application layer protocols and their associated ports. Hypertext Transfer Protocol, or HTTP, uses port 80. Domain Name Service, or DNS, uses port 53, and the Simple Mail Transfer Protocol, or SMTP, uses port 25. Click the first link on screen if you'd like to learn the differences between software ports, hardware ports, and IP interfaces. Click the second link on screen if you'd like to learn more about UDP and TCP software port numbers. Click Continue when you are ready to move on. Let's take a closer look at how the transport layer multiplexes data. On screen, 3 different types of data are coming from different application layer protocols. The 3 different types of data arrive at the transport layer, which multiplexes or combines all the different types of data into a single stream down to the IP interface. At the transport layer, a protocol like UDP or TCP adds a header to application layer data that includes a source and destination port number. For our current animation, we show the destination port number only. The source port number, which is not shown here, is a randomly selected number that uniquely identifies the connection on the sending side. The transport layer protocol then sends this segment or datagram down to the network layer. At the network layer, the IP interface adds the source and destination IP addresses. Again, for simplicity, we just show a shortened version of the destination IP address here. The network layer then sends the packet to the data link layer, where the layer 2 framing information is added and the data is transmitted. Notice that the transport layer allows multiple application layer protocols to share a single IP interface or IP address. At the physical layer, each of our frames is converted to an electrical signal and transmitted. Each of these frames is going to the same computer, but ultimately each is going to a different application layer protocol. On the receiving device, the process is reversed. The data link layer strips off the layer 2 frame, sends the IP packet to the IP interface where the layer 3 header is removed. The network layer sends the datagram to the appropriate transport layer protocol, which examines the destination port number, removes the header, and sends the data to the correct application layer protocol. At this point, the single data stream is demultiplexed into multiple streams going to the appropriate application layer protocols. Now that we understand how data moves between the application layer, transport layer, and lower layers, let's take a closer look at each of the transport layer protocols, starting with UDP. You might remember, in Section 1, we provided a brief description of the 2 transport layer protocols used in the TCP/IP protocol suite, UDP and TCP. Now we'll cover them in more detail, beginning with UDP. UDP is the simplest and fastest transport layer protocol. In fact, the specification for UDP is only 3 pages long. Like we saw with IP, UDP also adds a header to the data. The UDP header only includes 4 fields, 2 of which are the port numbers we just discussed. Move your mouse over each field to find out more information. Click Continue when you are ready to move on. You might remember from Section 1 that UDP is like dropping your letter in the mailbox and hoping for the best. Because the header only contains a simple checksum, UDP provides limited error checking capabilities and no recovery mechanisms. Even the checksum is optional. So in effect, aside from the multiplexing capabilities, applications using UDP interact almost directly with IP in the network layer. Because the UDP header is only 4 fields, the header and data together are often referred to as a datagram rather than a segment, hence the term datagram in user datagram protocol. After the network layer receives the datagram, it then adds an IP header to create a packet. On screen, you see 3 application layer protocols that use UDP: the Trivial File Transfer Protocol, or TFTP, the Domain Name System, or DNS, and the Simple Network Management Protocol, or SNMP. UDP is a connectionless service, meaning that UDP can send a datagram at any moment without any prior notification or setup procedures, sometimes referred to as handshaking. UDP just sends the datagrams and hopes the receiver is ready to accept and process them. UDP is also an unreliable protocol, which is not to say you can't count on it to work. It just means there are no guarantees that the datagrams will be delivered to the destination computer, and the sending computer has no way of knowing whether or not they arrived. If the datagrams are delivered, they might arrive out of order, or they might be delivered twice. Finally, with UDP, the sending computer transmits datagrams as fast as it can because no way exists for the receiving computer to tell the sending computer to slow down. In the example shown on screen, some frames were dropped due to network congestion. So why use UDP if it provides such limited error checking? Speed. Avoiding the overhead associated with sophisticated error checking makes UDP faster and more efficient for applications that do not need guaranteed delivery. As we've been illustrating, one example of an application layer protocol that uses UDP as its transport layer protocol is the Domain Name System, or DNS. Earlier we learned that DNS translates user-friendly computer host names, such as www.juniper.net, into IP addresses, such as 10.10.1.2. Notice that in this example, we're using an address from the private IP address space, not the Juniper network's public IP address. The client can then request a web page from the server using its actual IP address. Think about the last time you entered a URL in your web browser and how quickly the page appeared. That process uses DNS and needs to happen quickly. And if it happens to fail, no harm done. Your computer just tries again. So, how does DNS work at the application layer? When the DNS application on a computer needs to translate or resolve a hostname, also known as a domain name, to an IP address, it builds a DNS query and sends it to UDP. Without performing any handshaking, UDP adds a header to the message, which includes the well-known DNS destination port number, which is port 53. UDP also includes a source port number to which all replies should be sent. The source port is a randomly generated number that is not in the well-known or assigned port number range we learned about earlier. UDP then sends the datagram to the network layer. The network layer adds the IP header, including the IP address of the DNS server. Finally, the IP packet is encapsulated in the appropriate Layer 2 frame and transmitted to the DNS server, which is the computer that actually translates the domain name to the IP address. The DNS server, also known as a name server, searches its database for the requested name and sends back a response that includes the requested domain name and IP address. You can think of this database as the phone book of the Internet. The DNS application on the sending computer waits for a reply from the DNS server. If the sending computer doesn't receive a DNS reply, possibly because either the DNS request or the reply got dropped, it tries again, or sends the query to a different DNS server. Applications for which speed is more important than reliability use UDP. In addition to DNS, other applications using UDP include TFTP, SNMP, and many streaming video and audio applications. Now, what if an application needs more reliability than UDP offers? Then it needs to consider using TCP, the transport layer protocol we discuss next. Click the links on screen to learn more about these protocols. Click Continue when you are ready to move on. If UDP is like dropping a letter in the mailbox and hoping for the best, then TCP is like requesting the return receipt from the post office. To provide this type of service, TCP uses a sophisticated system of sequence numbers, acknowledgements, flags, and timers which UDP does not use, making TCP a more complex protocol. Let's first compare UDP and TCP. Like UDP, TCP provides a way of multiplexing data from different application layer protocols over a single IP interface. To do so, TCP adds a header to the data that includes a source and destination port number, just like UDP does. But the similarities stop there. UDP is a connectionless service, meaning that it can send a datagram at any moment without any prior notification or complicated setup procedures. TCP, though, is a connection-oriented service. With TCP, before two computers can exchange data, they must first agree to communicate and establish a connection. To form the TCP connection, the computers exchange messages in what is known as a three-way handshake. During this phase, the two computers agree on the parameters necessary to provide a reliable connection. While this connection is forming, no actual data is exchanged. Only TCP segments flow between the two devices. Let's look at a simple example. In this case, to load an HTTP web page, the PC must first initiate a TCP connection with the web server, specifying destination port 80, which is the standard port for HTTP, and source port 50,123. The source port is a randomly generated number that is not in the well-known or assigned port number range we learned about earlier. The web server replies, specifying source port 80 and destination port 50,123. And finally, the PC completes the handshake before sending data. Earlier we learned that UDP is an unreliable protocol because there are no guarantees of delivery. TCP, on the other hand, provides applications with a reliable data delivery service. TCP uses a sophisticated system of sequence numbers, acknowledgement numbers, and timers to ensure data arrives at the destination computer in the correct order without duplication. TCP uses a technique known as positive acknowledgement with retransmission, where the receiver of the data is responsible for telling the sender it received the data. We also saw that UDP interacts almost directly with IP, adding only port numbers and a simple checksum. UDP does not provide a way to chunk up or break data into smaller pieces to send across the network, relying instead on the application layer protocol in use. TCP, on the other hand, breaks a continuous stream of data into smaller chunks called segments for transmission across the network. Finally, with UDP, the sending computer transmits datagrams as fast as it can because no way exists for the receiving computer to tell the sending computer to slow down. TCP, on the other hand, provides a windowing system to regulate the flow of data between computers. With this system of flow control, the receiving computer can notify the sending computer when to speed up or slow down the transmission of data. A reliable connection, however, comes with a price. If we look at the TCP header added to each segment, you'll immediately notice that it includes 18 fields, significantly more information than the 4 fields added with the UDP header. The additional fields add extra overhead but provide the reliable service. Move your mouse over each field in the TCP header to learn more about its function. Click Continue when you are ready to move on. Next, we'll show how TCP uses these fields to guarantee data delivery. So what application layer protocols use TCP? The Hypertext Transfer Protocol, or HTTP, Simple Mail Transfer Protocol, or SMTP, and the File Transfer Protocol, or FTP, are common examples. Click the links on screen if you'd like to learn more about these protocols, or click the Continue. Now that we covered the basics of TCP, let's take a look at the protocol in a bit more detail. We just learned that before any data can be exchanged, 2 hosts must first establish a TCP connection using a 3-way handshake. The handshake establishes connectivity between the 2 communicating devices. In this handshake, the devices specify which port numbers will be used. The devices also use the handshake to synchronize the sequence numbers they will use so that segments can be tracked properly. We'll take a closer look at many specifics of TCP in this section, including this 3-part connection establishment process. We'll continue to use an example of a PC or client connecting to a web server. Earlier we learned that when a user enters a URL such as http://www.juniper.net into a web browser, the PC or client must first use DNS to determine the web server's IP address. The first part of the URL, http:// tells the PC which application layer protocol the web browser is going to use once the client knows the server's IP address. Because the browser is using HTTP, a TCP-based protocol, the client must first establish a TCP connection with the server. After the TCP connection is established, the client can now send its HTTP request. And finally, the web server sends the requested page. Click the link on screen to learn more about URLs, or click Continue to move on. Now let's take a look at what specifically happens in the process of loading a web page. After the user types in the URL, and the client uses DNS to determine the web server's IP address, the client must establish a TCP connection with the web server. The client starts the process of connecting to the web server by sending the segment down its network stack, as we've already seen, and the receiving device sends it back up the stack, where the transport layer strips off the layer 3 header to get to the segment. For our purposes, though, we're going to focus on what happens at the transport layer. Let's take another quick look at the TCP header. The highlighted fields are those that are involved in the 3-way handshake: source port, destination port, sequence number, acknowledgement number, ACK flag, and SYN flag. Now let's take a closer look at the handshake. To simplify our graphics, we'll portray the communications between the client and web server in columns for the rest of this section, with the client on the left and the web server on the right. The client initiates or starts the connection process by sending a TCP segment identifying the source and destination port numbers, in this case, source port 1146 and destination port 80, which is the standard HTTP port. Remember that before two devices can communicate, they must agree on sequence numbers in order to track segments and ensure reliability. To start this process, the client sets the SYN or synchronization flag to a 1. The SYN flag indicates that the client is in the process of synchronizing sequence numbers with the server. The client picks a random number for the initial sequence number and includes it in the sequence number field. In this case, the client begins with sequence number 0. So the first step of the handshake is complete. Now the server starts the second step of the handshake by responding to the client. Notice that the source and destination port numbers switch. Because the server is now the sending device, it sets the source port to 80 and the destination port to 1146, the port the client specified in the first step of the handshake. The client just told the server its initial sequence number is 0. With TCP, data can flow in each direction. So next, the server needs to tell the client its initial sequence number. The server turns on the SYN flag, indicating that it is also in the process of synchronizing sequence numbers with the client. Then the server includes its initial sequence number in the sequence number field. In this case, the server will begin with sequence number 101. The server also needs to acknowledge that it received the client's initial sequence number. Using TCP, a device acknowledges receipt of a sequence number by turning on the ACK flag and returning the next expected sequence number in the acknowledgement number field. In an initial handshake, the next expected sequence number is simply the initial sequence number plus 1. In this case, the server expects that the client's next sequence number will be 1. The segment the server sends back to the client is called a TCP SYN ACK segment because it is doing two jobs: setting the server's initial sequence number, which is the SYN part, and acknowledging the client's sequence number, which is the ACK part. With that, the second step of the three-way handshake is complete. The client responds with a TCP ACK segment, using the same source and destination port numbers it did originally. The client updates its sequence number by 1. The client turns on the ACK flag and acknowledges the server's starting sequence number by adding 1 to the server's initial sequence number, making it 102. The three-way handshake is complete. Now both devices have determined that they can communicate, identified the port numbers in use, and have determined the starting sequence numbers for tracking the data exchanged. Once a TCP connection is formed, the client's web browser can now use HTTP to communicate with the web server to actually send and receive data. Click the link on screen to learn more about the HTTP application layer protocol, or click Continue to move on and learn more about the TCP. Now, before we can discuss how data is transferred, we need to understand a key TCP concept. Application layer protocols send data to TCP as a continuous stream of bits. Earlier, we learned that 8 bits are a byte, and TCP only works with bytes. TCP groups bits into bytes and bytes into manageable chunks or segments that can be 1 byte or many bytes in length. Each byte of data sent over a TCP connection has a sequence number. Because each byte has a sequence number, each byte must be acknowledged. TCP uses these sequence numbers to acknowledge which data has been received, determine if data has been lost or damaged, and put data into the correct order. Let's now look at an example to see how TCP uses sequence and acknowledgement numbers to provide a reliable, connection-oriented stream of data. To simplify things, we'll just focus on sequence and acknowledgement numbers in our diagrams. The sender, which is the client in this case, keeps track of what data is sent from the data stream shown on screen based on byte count. Whenever the client sends data, it sets the sequence number to the first byte of data contained in the segment. So in our simple example, the client sends the first byte of data, setting the sequence number to 1. The client also starts a timer, which we'll discuss in more detail in a moment. When the server receives the data, it uses the sequence numbers to reconstruct an exact copy of the data stream being sent. The server then positively acknowledges the receipt by sending a TCP segment back, setting the acknowledgement number to the next sequence number or byte of data it expects to receive. So in this case, the receiver sets the acknowledgement number to 2, which is the next byte of data it expects to receive. When the client receives the acknowledgement, it notes that the first byte was received and moves on to the next byte. It sets the sequence number to 2, sends the data, and restarts the timer. Now what happens if the data gets lost or damaged? Here the client sent a segment with sequence number 2, restarted the timer, yet it has not received an acknowledgement from the server. When the timer expires, the client assumes the data is lost and retransmits it. In the example on screen, the server responds after the client resends the data. Luckily, TCP doesn't send data one segment at a time and wait around for an acknowledgement before sending another. Instead, TCP uses the sliding window method to send data, meaning that the client can send multiple segments without first waiting for an acknowledgement. The client has already sent and received acknowledgements for the first 2 bytes. Notice that we placed a window around bytes 3, 4, and 5, meaning that the client can send 3 bytes at a time without having to wait for an acknowledgement. Once the sender receives an acknowledgement, it will slide the window over and send the next byte. In this example, the sender transmits bytes 3, 4, and 5 and stops. When the sender receives an acknowledgement for bytes 3 and 4, it slides the window and sends the next 2 bytes. Remember that the acknowledgement number indicates the next byte the server expects to receive. Here the server has received byte 4 and is still waiting to receive byte 5. The sender will continue to slide the window as it receives acknowledgements. In this case, the window size is 3 bytes. The sender cannot slide the window until it receives the lowest byte number acknowledgement. We've just seen how the sliding window method improves network utilization by sending data without waiting for an acknowledgement. TCP improves the sliding window technique by also providing a flow control mechanism where the receiving computer can notify the sending computer when to speed up or slow down the transmission of data. How does this notification work? If we take another look at the TCP header, you'll see the window field. With TCP, the receiver uses this field to tell the sender how many bytes of data it can accept. In this simple example, the server initially could only accept 3 bytes at a time. If you remember, the client had already sent bytes 5, 6, and 7, but had not yet received acknowledgement for any of these. Here the server acknowledges sequence number 5 by returning the next byte it expects to receive, number 6. At the same time, it indicates in the window field that it can now receive 5 bytes at a time. This larger window will speed up data flow. As soon as the client receives byte number 5, the client slides the window over and increases the window size to 5 bytes. The client then transmits 3 additional bytes, specifically bytes 8 through 10, before waiting for an acknowledgement. The size of the window can change as conditions on the receiver or in the network change. If the receiver starts to become overloaded for whatever reason, it might reduce the window size by sending back a smaller number of bytes in the window field. Likewise, if the receiver has more available processor or memory resources, it can increase the transmission window size. Now that we know about the sliding window technique, let's see how TCP handles out-of-order segments. Remember that each byte of data has an associated sequence number that can be used to put segments back in the proper order. Let's say the client just sent bytes 6 through 10. Due to network issues, they arrived out of order at the server. Not a problem. The server uses the sequence numbers to put the data back into the correct order. To keep things simple, the first few examples only showed 1 byte of data being transferred at a time when in fact TCP can put hundreds or thousands of bytes in one segment. The example also only showed data flowing from the client to the server. Luckily, TCP supports full duplex communication, where both sides of the connection can transmit and receive data at the same time. Let's see how this works. If you remember, during the 3-way handshake, both sides agreed upon their starting sequence numbers. Here the client's starting sequence number is 1, and the server's is 102. Next, the client sends 495 bytes of data, setting the sequence number to 1. Notice that the acknowledgement number is still 102 because the server has yet to send data. If the server is transmitting its own data, which is the case here, it sets its sequence number to 102, indicating the beginning of its data stream. In this case, the server is sending 597 bytes of data. The server acknowledges receiving the client's first segment by setting the acknowledgement number to the next sequence number or byte of data it expects to receive, which in this case is 496. So the server is actually telling the client it received bytes 1 through 495. This approach of using separate sequence and acknowledgement numbers allows both devices to simultaneously transmit data and acknowledge transmissions from the peer device. After receiving the acknowledgement, the client has more data to send, so it sets its sequence number to 496. Notice that the server's last acknowledgement number and the client's next sequence number always match. Client acknowledges receipt of the server's data by setting the acknowledgement number to the next sequence number or byte of data it expects to receive, which in this case is 700. So at this point, the client has received bytes 102 through 699. This slightly more complicated example shows how full duplex communication works with TCP. It also shows that segments can contain hundreds or even thousands of bytes of data. When the client and server are done communicating, TCP closes the connection. Ideally, TCP uses a modified three-way handshake. Remember, the TCP connections are full duplex. We view them as two independent data streams, one going in each direction. In this example, when the application program on the client tells TCP it has no more data to send, TCP closes the connection in one direction only. The client sends a segment with the fin or finish flag set. The server acknowledges the client's fin, but does not immediately close its side of the connection. In fact, the server might still have data to send to the client. When the server is done sending data to the client, it sends a segment with the fin flag set. The connection is finally closed when the client acknowledges the server's fin segment by sending an ACK segment. In this section, we've explored the difference between two transport layer protocols, UDP and TCP. By this point in the course, you should now be familiar with what happens at every layer of the network model and understand how data from an application on one computer is routed through networks and ultimately arrives in a format ready for use by an application on a receiving computer. In just a moment, you'll have a chance to test your knowledge of UDP and TCP. Then in the final section of this course, you'll have a chance to apply what you've learned in an interactive